all, which is generic type inference during function calls, because it's difficult, gonna slow things down. I'm not that interested in doing it. I generally am a fan of annotating types rather than type inference. I think type inference um, can cause, both the programmer and the compiler developer a lot of problems. But there are some places where it makes a lot of sense and that I do believe in it. Um, one of those places is in closures or lambdas, where the type of the argument is very obvious from the context. Like when we're calling map on an array of integers. Okay, that closure, that lambda needs to take an integer. We shouldn't need to annotate it. This to me is a little bit different type of inference than more general, I'll infer the type of your function, especially when the type system is more complex. Say there is a lot of polymorphism or even inheritance involved, and we let the compiler infer a lot of things, then types can just not be what we expect them to be. Things can get slow and more complex than they need to be. But there's this really simple case that has been a big pain point as I was trying to write some code in this language here that I thought I would solve, because I wanted to, and it also forced me to clean up the way I was specializing functions as well. So let me just go ahead and show you the problem I'm talking about. We have a program here called generic inference, and I can go ahead and run this. If we run the compiler with -- run, it just means run the program too. Compiler doesn't really have any business running the executable, but it's just convenient, and it was that way from the beginning, so I just have it here. Anyway, this program runs, and it compiles is the important thing, but it also runs, and I'll put 0. There's no assertions, but we can see that it compiles and type checks, which is the big deal, because we're doing some funny stuff here. Well, we have 2 arrays, and so here's another place that I am doing some inference, and I'm not sure if I like this or not. I think there's places for it. So anyway, we will infer the type on local variable declarations. We will never infer a function's return type. Anyway, we have 2 arrays of integers, and then this is should really be in this order. We want to call .length on x's, but length is a generic function because the array is generic. And I know there's other ways to implement generic data structures, but this is the way I've done it here. So this is what I'm left with. Every function is just a generic function, right? This isn't really very right. I mean, this should probably be up here. I understand that. And it should be forced that we're referring to the same t throughout, although I'm not sure it really makes much of a difference once we get into the actual implementation. But anyway, these are just functions that take a type t and then a self that's of type array of t. If we look at length, it's no exception. It takes a type because we need to know what type the array is, even though we never use t. And so it's very annoying because I just want to call length, and the type actually doesn't matter here, but I have to pass it, and the code starts to look pretty ugly. The desugared version of x's.length int empty paren is, of course, this array length, where the first argument is x's, and that looks more like what we see here, right? There's a self parameter or argument that is first that is implied. So x's is passed here. These do the same thing, but we want to make sure that both work. It helps me to have it written out as I was thinking through how we do this inference. We have some more complicated functions. We have identity, which actually uses t twice. Identity, since x's is an array event, I have to pass this. In the current world where we don't have inference, I had to pass this, and then this combined length function. So wouldn't it be nice if we didn't have to pass these? And let me go ahead and turn this thing on. The key. Okay, let's put this somewhere helpful, not on my face. What if we put it, down here? Yeah, perfect. Okay. So we've removed the type annotations. Let's compile again. And it still works. So this is all I wanted. Now I'm going to go ahead and disclaim this. This does not work even for this simple of a transformation of the case. So it's hard-coded to understand two type patterns. The first type pattern is where the type variable is used raw, I'd say, like lone in the prime position. The parameter is the type variable, and the other case it understands is array of t. Now it could also easily understand any single argumented, any unary arg data structure, but I actually don't have them. I don't have generic structs yet, only the built-in array. So it understands array because it's built in as a type. So, you know, if we even look at our type enum, array is here. It's not implemented as another data structure. So those are the two patterns we understand, and this actually works. It doesn't understand optional yet. It probably will need to soon. That one I can also hard code. And I think I'm in a position from here to actually make the algorithm recurse and go deeper, and it wouldn't be too bad. But it is a little bit dicey, and all I wanted was to implement these simple cases so that the code looked nicer. So that's what we have right now. And I'll go ahead and dive into the code that accomplishes this. So this is where we are in the type checker. So we've already parsed the program, and we know well, let's go ahead and open generic inference, my bad. So we know we have a call to a function. And we've actually already done this desugaring from x's.length to array length x's. We kind of have this, and that's what this expr came from. So if it is a method call, we already actually evaluated the first arg, the self, because we had to do that. And this has been given to us. So now it says, okay, take me from this function call AST node to a typed expression. And the expression is going to be a function call. Yes, a call. So a call, most importantly, it refers to the function it's calling by an ID of a real function, not of a syntax definition of a function. We have the arguments that have been type checked as expressions. We have the return type explicitly in there. And then we have a span location info. So how do we get there? We first check if this is a special case, how we implement the sum optional. It's syntactically looks like a function call, so it's implemented here. Maybe it could be moved one level out, but we're not going to worry about that right now. So first we need to know what function's being called. So we resolve function call, and this takes the call, this expr, and what scope we're in, and then we either get back an expression for another special case. It's not actually a function call, surprise, it was something else. Or maybe an intrinsic, I'm not sure, we'll check. Or we get a function ID back, and we're going to call that function. Thing is, if we get the expr back, we just short circuit back up. So what is the case where we short circuit with a left? Right function ID. We'll look for either left. Okay. Okay, so I recently implemented optional.hasValue as a special case. When we resolve the function call, we just do it. This is pretty hackish for internals. So this is if we had an optional boolean sum 42.hasValue, that's what that is. But every other time we get back a function ID, there's a little bit of a tangent. So we have a function ID, and we're going to look up the function. We're going to look that function up. So we can assume that we've already, yeah, find function. Did I ever call eval function? No, I'm not remembering how my compiler works. We must have already called the eval function. Yes, so all the functions that we're going to call, we hope have already been eval. It's a one-pass compiler right now, so we're hoping that there already is a function that by ID that's been type checked for this call. That maybe should be a separate pass. So anyway, we know what function we're calling now. We're going to look that function up so we have the actual object, not just the ID. We're going to do some cloning because of Rust, just of tiny params objects. And now a big if. So a big if it's generic, right? So if it's not generic, we're going to do something pretty simple. We're going to call type check call arguments, passing in a bunch of stuff, passing in the original params, which we haven't looked at yet, but it's just the params that the function takes because it's not generic. The scope ID, not to skip type check. This is the flag I just added for this generic type inference. So that gives us back a vector of typed expressions, right? And a function ID. So why does this have to give back the function ID? Well, it's because in the other case where it was generic, we're doing something a little bit different and we might make a new function. So specialization is what happens here where, let's say you call identity with int. Well, we're actually going to stamp out a function identity int, right? And then we're going to stamp out identity array. Oh, this would be, identity array int would really be more, it's not generic, right? So it's fully concrete. There are no t's, there are no type variables, right? So that's what specialization means. So obviously, you went to call identity and we specialized, we made a new version of identity for array event, right? We need to give back the function ID of that function to the caller so that it's calling the right function. When we go to code gen, we need a fully concrete function to call. So that's why we might give you back a different function if it was generic than if it's concrete. Well, then this is simple, right? Just to go to the rest, we're going to set the return type. I'm not sure why we don't already have that or copy that higher. Oh, we need the return type of the specialized function because guess what else might have changed? Not just the params, but also this. This went from t to int. So you got to be sure and do that. And then, okay, we return the function call. So let's zoom in now. We've really looked at everything except for what happens when it is generic. And I hate that this is wrapping. Can I just... Yeah, it'll be okay. All right. So intrinsic type we can ignore. This is for built-ins again. Anything in the prelude marked as intern is implemented intrinsically by the compiler. You can't implement it in the source language because you can't malloc, for example, for array new, things like that. So if it's, whoops, let me go back to the typer. Apologies, and I lost my keycaster. Okay. All right. So this process of specialization, how do we know when we call a function if we need to stamp out a concrete version of it? How do we know if we need to specialize? Well, the way I check this is I say, is every parameter not a type variable? So if we're calling identity, x is of type t, boom, type variable, okay, we need to specialize, right? But let's say x was int, okay, we'll go to y, yt, boom, type variable, right? It's not enough just that it takes a t, right? Because it might not be used. So yeah, we look for type variable. But what if it was array of t? Well, we could check if it's array, then does the element type contain a type variable? So I can recurse here. I'm not so afraid. So for each type argument, Okay, so I suppose we're not actually, I was a little bit inaccurate. We're not looking through all the params. We are looking through all of the type arguments. So for each type argument, we're checking if it's fully concrete or if it's generic. So the way we do that is for each type arg, we say is generic. And this is the algorithm that I just explained. So for concrete types, they're not generic, they're concrete. For an array, it's generic if the element type is generic. For a record, we don't support yet, but it would be if any of the element types are generic and so forth. So we just sort of recurse down there. This would be something that if it ever got expensive would be really easy to memorize, to cache. We have a type ID function from type ID to bool here. While it seems like a lot, I don't think it ever really could get slow just because how deep do your type hierarchies really go? Even if you had 15 sort of nested structs, which would be quite a lot with generics, I still don't think this would get that slow, but yeah, you would probably eventually want to cache this just because it is recursing. So we say fully concrete true. If we find a generic, we say fully concrete false. So, and now we have another sort of if. So if it was fully concrete, so what's happening here is we have a function that takes type params. So it was a generic function, but all of its, we have all the params and they're all concrete. So we can skip type check. Just make sure I'm saying the right thing and not saying things backwards. All right. If it's not concrete, then we can just type check this like normal. We don't need to specialize yet. We don't need to stamp out a function. There's still something generic, so we just want to let the generics flow through. We're still going to type check. So even though there's a t here, we can still check that like length exists. We can still check these are ints, right? That's fine. We're still going to type check. It's not like C++ templating where the generic code is just fully free, right? But we're not going to stamp out a new function. Okay. But if it is fully concrete, then we're going to get specialized function for call. And this isn't really about specialization. It was supposed to be about the inference, but long story short, by now, whether we inferred the type args or whether we have them, we're now just going to make a copy of the original function where we substitute in the actual values for each of those variables, add them to the scope of the function. So we actually do this just by adding each type param to the scope as a variable, right? So that then when we're evaling this function, we're gonna look through, we're gonna see t, look it up in scope, we're gonna see int, and then the actual type check is going to substitute in int for t everywhere, and that's how we would get our specialized copy of combined length. We would get combined length int, erase the param, ICT. Oh, is t point to anything? Yeah, right, because specialize, there's a specialized flag that's set to true. Can do that right here when we eval function, which is like type checking the function. This is our new copy where we've set up things in the scope and we say specialized true, so it's expecting to do that. So a little rabbit hole there. Let's go back to when we call, get specialized function for call though. We're passing in these type args, inferred or passed type args. So where did these come from? I skipped over this line. This is the whole point. So if we're generic, we do the intrinsic type, and I jump straight to here. So we need to infer the type arguments or evaluate them if the user has supplied them. This is what we just added. This is why we can do this or this. So what happens in infer call type args? So we still have the call, the original function, the generic one, this expr, and the calling scope. What is the process here? Well, really some setup, mostly to get around borrowing rules, looking up the function, getting the fields we'll need out of it so that we don't have a self borrow lasting for the whole function, because we need to call functions that take mute self. And now we get down to here. So let's match on the AST. So this is the function call as the user wrote it. And we can see they either can pass type arguments or they can skip it. So if they passed them, then we're just going to type check. We're going to make sure it's the right number of args. And then we're going to go through each one, and we're going to evaluate the param, and then we're just going to push it. We don't even support constraints. So a constraint would be like if we said t has to be sized. Well, not question mark. T has to be sized, right? That would be a constraint. We would then check, okay, they passed int. Is int sized? We don't even support constraints, so there's really nothing to do except evaluate this type expression and then push it to check params. So that case is simple. Here's our inference case. And I have an old comment here, but I think it's still sort of true. I think this is what I ended up doing. We find arguments that include a type param, and we find the actual value passed for each. Find where the variable appears within that expression and assign it to the concrete type. So that is what we do. So essentially what this looks like is if we have array length x's, we're trying to solve for t. And it is like solving an equation. And I know there are well-established algorithms for doing this in a really sophisticated way. I'm just explaining what I did sort of on my own, thinking, what's the simplest, most straightforward way I could solve this problem. So t is something. So we have a function definition, and we have x's. Yeah, this is the definition, right? So how do we solve for t? Well, there's not much more we can learn from here. So let's move to the actual params, and let's look at the first one. Okay, the first param is going to be an array of t. So I see that I was passed x's here. So I know the type of x's. That's already been evaluated. That's my typed expr, this expr that I already have. So I can say, hey, let's get the type of this first param, and we're going to get back array, and we're going to get back array of int. Okay, so say, okay, x's is array of int. And okay, array of int. What's the definition? So we're comparing array of int now with array of t. Let's go ahead and put in what was given. So array of int was given, and I go back to the definition and I say, oh, I needed an array of t. So we line up where the t is something else, right? And we say, okay, t equals int. T equals int. And then we actually push solved params. We kind of push. We say, okay, we solved t. It's int. Let's keep going. Because let's say you passed different with combined length. We'll do bools. Val bools. True. True, false. Okay. Let's say we did this. Then let's go move on to the next one, right? So we have x and y. So x, let's not use length. Let's do combined length. So we're trying to solve for t. Okay. X is array t. Y, array t. And we already did. We did t equals int. We would do the same thing, right? So we'd push that. And then y. Okay, well, let's look up. Well, what did they pass for y? They passed bools. Bools is an array bool. So we line up array t, array bool. T equals bool. Okay, t equals bool. Now let's check. Did we solve as many params as we have? Well, no, we actually solved 2, but we only have 1, right? Oh, they're mismatching. And then we can complain, hey, we have we solved mismatching type params. I think we do that down here. Conflicting type parameters, right? And maybe we'll try and get this error. That would be cool. I did get this in testing. So I don't actually implement it this way. I actually just check before I push the second one, and then I short circuit out. So I would, as soon as I see bool, I say, hey, did we already solve t? And if we did, then I just fail. Um, Again, you could probably go out of order and then unify things and figure out the solution. This just goes left to right. Um, you could always, I guess, try again in the other order and see if it doesn't conflict. I'm not sure. So back to the simple example, we yeah, and for identity, it's sort of the same thing, except the pattern matching is a little simpler because the pattern would have just been t, right? And we would see, okay, we need a t, we got an int, and then t equals int, push that, and then we go. So let's look at the code for this. Really, it's really simple. For each expression, get the param. So the expression here, x's, right, which points to an array event. The param, being x's array of t, right? So you have, I should have named these differently maybe. So you have the x's array int, and then you have the x's array t. They're lined up. Okay, so let's get type of the param. So that's the thing that was actually passed. Is it a type variable? Okay, well, then we're done. Then, they passed a param. The type param is a type variable, so put it in. If it's an array, and the element type is a type variable, and what was passed is an array, then we've solved the array case. So this is very naive, just a little matching. We could probably convert this to just recurse somehow. I haven't really thought it through yet. I'm not really interested. I kind of want to do some other features. But the point is that all you would have to do is expand this. All the information is here to match larger patterns, and we would be good to go. And importantly, this would work with two variables. It does with like a key and a value, like for a built-in map, which is something I want to implement next, built-in hash map. So I just wanted to make sure it worked and that it worked for two variables, and so I'm pretty happy with that. So yeah, we type check our solve param. We make sure that they don't conflict with each other. We solve the same one twice, and that's it. So that was infer call type args. So we call that if the user didn't give us. No, we call it either way, actually. So it's not always inferring. It's only inferring if they weren't given. It's sort of an infer or type check call type args. So we call that not an eval fun call. We call it here. So now we have the type args. And now we can go ahead and say, do we need to specialize? This needs to happen first, because until we know if t is int or t, we don't know if we need to specialize or not. So this is almost complete. There's one last issue, and the issue, well, there's probably a lot of issues, but there's one that I'm aware of where I was solving this year's Advent of Code Day 1 here, and the solution is not nice yet, but we're working on it. We need iteration. Iteration is killing us here. We're just using I and resetting I, so it's it's not very nice. But on this line, we're doing something fun. So we're pushing to an array of events. I need to think through if even this is going to break my inference. No, because the pattern is only array int. So I think we're safe anyway. So we're pushing an element, and the element type is array event, and that's fine. We can infer that, but I'm calling type check call arguments with this skip type check. With this skip type check true. Yeah, so here, the reason we're skipping type check, so this is the case where we're inferring. So we want to eval all these expressions. but we don't yet know what type we're expecting. So, right? So what we're doing here is x is dot length, right? I want to know what type this is, this term, so I need to evaluate it, right? But I don't necessarily want to type check it against the definition array of t because I don't know what t is yet. So I'm reusing the code to line up the arguments with the expressions and evaluate them and sort of type check them, but I'm not actually failing if they don't type check yet. I'm just using this to get the typed expressions. It's a little bit of a hack, but it's a lot of code. And I think it's actually correct and perfectly fine to do this. But the issue, while I am skipping type check and skipping, see, if not skip type check, then we don't call type check types and then fail. This is for self, which is handled separately, and then this is for the rest of the arguments. If I run this program, AOC1, see, I get conflicting type parameters. So here's our message. For type param t and call to push. Expected array int but got t. So this expected but got, these are the two things I solved for t. I solved for t twice. First, we solved array int, and second, we got $t, which is just how I'm pretty printing type variable t. So why did that happen? And that happens on this line. So again, we can read this as array push digits and then this array. So, and there's a t here, and push takes, this is the most interesting of the cases looked at because this is the array of t, and then this is actually of type t. So we're using t twice and in different positions. We definitely figure out that t should be, well, that t should be array of int. Again, this t, so sorry, digits of type. Array push. Yeah, let's just go ahead and check the definition of push real quick. Yeah, self array t. Okay. So what's happening here is that I have this type hinting where when we type check, when we evaluate an expression, we can pass in what type we expect it to be. And this is mostly so that we can do things like if I have b and it's an optional bool, I can just say none. And I don't need to specify a type on the right-hand side. What happens is we eval this with a type hint of optional bool. And if there's a type hint and we have a none, then it works. So the same with, say, an empty array, right? We type hint that we expect a bool actually in the first arg. So if I put 1 here, you know, that just fails immediately. And so we can infer better, right, by having these type hints. So because this is a call to a function, I'm actually type hinting for the, so in push, we have self and elem. So on elem, when we evaluate that expression, we're passing in a type hint of t, and t has been solved to be, t hasn't been solved yet to be array of int. So, because we're evaluating these before we're doing the inference because we need the types of the arguments. So we're hinting at this thing that it should be of type t. So even though this expression on its own has type array of int, when I call evaluate expression on it with a type hint of t, it comes back and it says, hey, I'm type t. So that's the bug. It doesn't really make sense that it would be of type t, right? It should probably even just reject that type hint. But that's the bug. So I hope that makes sense. The fix, one thing that fixes it is to move this list, this as digit C single element array up on its own line and annotate the type and then call push. That actually works fine. But you're working around a compiler bug for sure there. So I thought I would just fix it. So this type is fine. It's these others where we call eval expr. So evaluate expression, and this is where we have an expression from the syntax tree as written by the user, right? And we're turning it into a typed expression. So, and it takes an expression, what scope are we in, and then an expected type. This is that type hint I was talking about. And we do things, like if there's an expected type, okay, so this is the recursive case. If there's an expected type of option, then we can lift the value, things like that. So we just don't want to pass a type hint when we're only calling this to get the arguments. So let me go back to type check call arguments. So this one here, so this is called expected type. So let expected type for param. So now if skip type check, it's none. We just don't want to hint at the type at all. And this does mean that you won't be able to use the type hint for a generic function, but it's kind of like, which one do you want? Do you want to give the types and let me infer the argument of your params, or do you want to pass concrete params, even if you just use descriptions, so that I can infer the type of the call? Else the param of the ID. So we'll just change in argument here. Good old CIA, expected type for param. Thanks, Rust. Yes, yes. I love these little braces. Okay, and I think that fixes it. So if it doesn't, I don't have the energy to fix it tonight, but that worked. And that actually is the solution to my part 1 of this year's Advent of Code Day 1, which is pretty exciting. So I made it a lot prettier. You can imagine how this looked before, right? Where every call to length, every call to push was full of this array. Yeah, these type annotations. So I'm really happy with that. I can go ahead and walk through this solution while we're here. I'm not proud of how a lot of it looks, but a little bit of it I am a little bit proud of. So these should be in the standard library, but we do have a first and last for an array. Maybe head, I don't know. I kind of like just first and last. Don't want to get too functional in the standard library names. You want it to be accessible. I think first and last is probably great, but it's kind of a nice little expose, we have, or expo demo, we take t, we take an array of t, we return an optional t. If the length is greater than 0, then there's definitely a last element, and we return it. Otherwise, we return none. This, is pretty nice because this none, the type of this none, is inferred from the type of the conditional, right? I mean, I call this the consequent branch. So the then branch, consequent, the then branch, and the else branch, the consequent and the alternate. So the type of the none is passed in as the type hint from, so it says if the hint is here, and yeah, it should be here. So we propagate the optional. This gets lifted into an optional t because of the type expected here. So it's actually, I spent a night getting this to work without sort of just defining a separate val or providing explicit type, and this is why, I didn't want to do much type inference stuff, because it starts to compound and it gets really tricky. But anyway, it works. It works nicely. So we have first as well. It gives you the first and is digit. We convert this character to its ASCII code, and then we can just check the actual range. We don't need to call that ret. We could just do this for sure. I realized that GTE and LTE weren't working when I did this, so I had to do the exclusive version. As digit, really it would be cool if this just returned an optional and it checked the range and then did it. So because I have to do is digit then as digit, and then we could just match on it. Maybe we make that change right now, which would be fun. But anyway, we can keep going. This is the ASCII code for a new line. It's the only way. I don't have character escapes. So I have chars, but I can't do that because the parser actually expects them to be one character and it goes and gets that one character. So yeah, we need to implement those. But for now, I do the ASCII code, convert it to a char, convert it to a string. So that's terrible. We have standard library, fun, function, files, read to string. This works. You know, we can now print the file was print int characters long. Run it again. That's pretty exciting to me. Silly, simple as it is, that represents a lot of work. We're linking against a program written in Zig that knows about our string type. We're using Zig's file system here, main.zig. So this is export fun and x read file to string. It only supports 10 megabytes apparently, but that's okay. This is how our string data structure is actually laid out in memory. We have a length and a data pointer. Yeah, and it just works. Okay, so we make an empty array and we start iterating over the characters. Every time we see a new line, we increment line. I would love to just break it into lines first. It's not good code, but it's what I have, and all I have are while loops, so that's why we're iterating this way. If C is a digit, if it's the first, then we push it. Otherwise, we expect there to already be an array here, and we push to that array. So here we're pushing to our digits array, and here we're pushing to the element at line in the digits array. So we're pushing a single int versus pushing a new list of ints, and this just works, which is, nothing short of a miracle. So, and then we got to go back through. We get the first and last digit from each line is what this puzzle is, and then we take them and we combine them. We don't add them. We combine them as if it's a decimal number. So we could take them as characters, convert it to a string, and convert the string to int. But it's actually a lot better to just take them as an integer, multiply the tens, the one in the tens place, by 10, and then add the last. So that's what we do here. We take the first of digits at I and we take the last. This is of type optional int, which is really nice. I'll go ahead and type this one as bool just so you can see some failed type checking. Local variable type mismatch. I'm dumping the whole program, but this is our actual output. See, so expected bool but got optional int. So we'll go back to optional int here, and we're just force unwrapping these because we know it's not empty. We could actually match instead. I can do if first and call it list, and I can do if last and call it list. This is our binding if expression. Copilot needs to get off my back. Yeah, we would just do it all in here. So let's try that. So the whole point here is we didn't need to do the forced unwrap. We can just list. The bang, of course, if you hadn't figured out, that's like dot unwrap, that's like dot get, that's like, give it to me or crash with an optional. This checks if the optional has a value and then gives you a binding of your choosing. This is just like Zig, where the type of FST is int, the type of first is optional int. So let's try it this way. and it works. Just to show val lst. I wish I could print the type of something, but that would require like the type info existing at runtime in some way, shape, or form, which would be a lot, but it would be really fun. Can I do this? Can I insist it's an int option and get a mismatch? No, it'll actually just lift it for me. So this is just lifting this right back into an optional, which makes sense. What I really want to do is a type assertion. Anyway, yeah, thanks for watching. That's a little demo of where it is right now and some generic type inference for dummies. So I hope you enjoyed it. Yeah, tune in next time. Maybe we will implement a nice feature.